Hi everyone, welcome to section 10.2 where we start solving right triangles. When we ask you to solve a right triangle, what we're trying to do is find all missing sides and all missing angles. So if there are two sides missing, let's say, we would be looking for both of those side length measurements, or if you had an angle that was missing, we would be looking for you to calculate the size of that missing angle. In order to solve a right triangle, we're going to be using sine, cosine, and tangent ratios along with Pythagoras' theorem. Now, in order to help us organize the information, we should be using a table to help assign our variables or find those unknowns. Sketches also become really important so that we can label sides appropriately. So it gives us an opportunity to find the sides opposite and adjacent over and above knowing clearly which side length is, let's say, the hypotenuse. So to help work through this, let's take a look at example number 1. It says solve triangle ABC if angle C measures 90 degrees, A is 20.2 units, and lowercase b is 11.4 units. What I want to remind you of are some of the norms for naming. We have capital letters for angles, and we have lowercase letters for side lengths. So if we want to solve a triangle, we're actually going to be looking for any missing parts. We know that ultimately we want angle A, we want angle B, and we want angle C, which is given already, 90 degrees. We also want all side lengths. So A has been given as 20.2 units. Our B side length is 11.4 units, and C is going to be an unknown. So what we have here are two missing angles and one missing side length. So order doesn't matter in terms of what you'd like to solve for first, but a sketch is going to be extremely helpful here to help us to organize this information. And the sketch might not be to scale. We don't really know what those missing sides or angle measurements are, so you can draw a triangle just assuming that it's not to scale initially here. So we've got angles A, B, and C. I know C is the right angle, and if I were to label my other side lengths, A is opposite angle A, so we have 20.2 units along the base of this triangle, and B, lowercase b, is 11.4 units sitting opposite angle B. So if you wanted to get the third side out of the way, we know we can use Pythagoras' theorem in order to do that. So we can say a squared plus b squared is equal to c squared. So a is 20.2, but again, that needs to be squared, plus our b squared value of 11.4. All squared again is going to be equivalent to c squared. So this just becomes an exercise in calculation. 20.2 squared plus 11.4 squared gives us a total of 538, but that's our c squared value. So remember, when we're talking about side lengths, we want to have just c. So the exact value of c would be the square root of 538. We know we have to square root both sides, but in this kind of situation, we're not really talking about negative roots because we're not talking about negative length. It doesn't make sense in the context of this question. So side length C is exactly the square root of 538, so you could put that in here. But when we're talking about measurements, sometimes it's a really good idea to compare that side length to the other sides and make sure that, for example, the longest side is across from the longest angle. So if you approximate that, we get roughly 23.2 when we type that into our calculators. So it's definitely the longest side, and it's opposite the 90-degree angle. So far, things are looking pretty good. What we want to find next are the missing angles. And if we just go alphabetically and say, let's find A, I'm going to mark A as my reference angle so that I can clearly see which sides are going to help. Now, although I have all three sides, it's probably best for us to use the two given pieces of information just in case I've made a mistake here. So if we're going to use the two given pieces of information with A as a reference, 20.2 is going to be the side opposite and 11.4 is the side adjacent. So if you go back to your SOHCAHTOA, sine, cosine, and tangent, you want to be looking for the ratio that involves both the opposite and adjacent sides. What we see here is that's a tangent ratio. So we can say the tangent of angle A, so you always have to have the type of ratio it is next to the angle. So tangent of angle A is going to be our opposite side of 20.2 divided by the adjacent side of 11.4. So in order to find angle A, which is our task here, we need to use an inverse function. So from the previous exercises, we realized that if we want to find an angle on your calculator, you have to find the inverse. So tan inverse of 20.2 divided by 11.4 is going to give us that angle measurement. Now you want to make sure that you are in degree mode when you do this, because if you're not in degree mode, you'll get a very different answer. So the tan inverse of 20.2 divided by 11.4 should give you roughly 60.6 degrees. So A is approximately 60.6. Now we can put that in here as our missing angle measurement, but we still need to find angle B. There are two ways you can do this. If you want to just add up angles A and C and subtract that from 180 degrees, because we know the sum of all three angles needs to be 180 degrees, or you can go through another trig ratio in order to solve for B. So let's do that just to practice. If I were trying to solve for B, I'm just going to change my color here. If I were trying to solve for angle B, I'm going to change my point of reference. And as soon as I change my point of reference, the opposite and adjacent sides will exchange. So what happens here, we'll put angle B back, is the opposite side becomes 11.4 and my adjacent side is 20.2. So if I wanted to find angle B, then the tangent of angle B is going to be opposite over adjacent, or this time 11.4 over 20.2. Now, to find B, we're going to say that must be found using an inverse function. So we have tan inverse of 11.4 over 20.2. So once again, be very careful with your calculator work. We want to make sure that you are using your inverse and you are in the right mode. What you should get this time is 29.4 degrees. So the good news is you can use your understanding of the interior angles of a triangle to make sure that this makes sense. So if I take these measurements, and these are approximates, by the way, so I could be using approximation symbols here. What I want you to recognize is that the smallest angle B is across from the smallest side length, which is 11.4 units. And that's typical. That's what we should see. The largest angle of 90 degrees is across from the largest side. And if we found the sum of all three angles, we know those angles will sum to 180 degrees. And again, that's what we're predicting, because these are the sum of interior angles within this triangle. So we have solved this triangle by finding all missing side lengths and all missing measurements. Example number 2 is giving us a new triangle to solve. So once again, it's triangle ABC. I can put the angles on one side. We know that C is 90 degrees. Angle B is 62 degrees, so we'll be able to very quickly find angle A. But we also need to make sure we have all side lengths accounted for as well. So in this case, they're not labeling the side lengths the way we traditionally would. So this is where a picture comes in really handy. If we were to sketch this triangle, and again, it may not be to scale the way I'm sketching it, but that's okay. We just need to make sure our labels are in the appropriate spots. So we have a 90-degree angle measuring with angle C. We have 62 degrees as your measurement for angle B, and we have side BC measuring 7.1 units. So that means the side between capital B and capital C. So we know that 7.1 is sitting here. Now, if we were to use lowercase letters as side lengths, we know that that's lowercase a. So side length A is going to be 7.1 units. Now we have to find our approximations for B and C and finish filling out the angle measurement. So the angle that's missing here, of course, is angle A. I might as well get that angle out of the way because it's the quickest and easiest thing to do. So if I want angle A, I know I can take 180 degrees and subtract the two given angles. So we can subtract 90 degrees and we could subtract 62 degrees in order to get your angle A. So we've got 90 minus 62, so 28 degrees is the amount for angle A remaining here. So A is 28 degrees, and we're ready to start tackling missing side lengths. So the unusual part about this question compared to the last example is we're missing two sides. We can't use Pythagoras' theorem in order to find those missing sides because I don't have enough information. We actually need to use a trig ratio in order to find these missing sides. So pick a letter first. Let's say we're talking about finding side length B. What I like to do is also pick my reference. So my reference angle is going to be 62 degrees because that's the angle we were given. That's the one I'd like to work with. So if 62 degrees is the angle given, we know that B is going to be the side opposite, or if 62 is your reference, B is the side opposite. 7.1 is going to be the side adjacent. So the ratio, let's jot down our SOHCAHTOA. The ratio that holds together the opposite and adjacent sides is tangent. So I'm just going to write the tan ratio in its original form and say the tangent for angle B is going to be the opposite side divided by the adjacent side. Now I can fill in the information that I know for sure. I know that angle B is 62 degrees, so I'm going to type or plug that into my equation here. So tan of 62 degrees is going to be the opposite side of B divided by the adjacent side, or 7.1. All we need to do is solve this little equation. This little equation happens to have a fraction in it. So if we want to clear the fraction, what we can do is multiply both sides by 7.1. So if I multiply the right side by 7.1 to clear that fraction, I must multiply the left side by 7.1 as well. So what we get here, what we get here is a B value that we can find by taking 7.1 and multiplying it by the tangent of 62 degrees. So we have all the information we need. We just need to plug that into the calculator to get our final measurement. So 7.1 multiplied by the tangent of 62 degrees is roughly 13.4 units. So B is approximately 13.4. Now that makes good sense so far because the smallest angle was 28 degrees and the smallest side so far was 7.1 units. 62 degrees is much larger than 28 degrees, and we see the side length is much larger as well. So we found side length B, and now that we have two side lengths, truthfully, we could use Pythagoras' theorem, but I always like to go back to the information that we have been given, and I like to use that as much as possible. So we can still keep angle B as our reference, we can still use the adjacent side, but if we want to find the hypotenuse, then the ratio tying those together, tying adjacent and hypotenuse together, is a cosine ratio. So what we would say next is that the cosine for angle B as our reference is the adjacent side divided by the hypotenuse. So again, cosine of 62 degrees is going to be the adjacent side of 7.1 units divided by the missing hypotenuse, which we can call C. So this is another sort of equation with a fraction in it. So we can clear fractions. If you're comfortable with sort of a cross multiply and divide process, you're welcome to do that as well. Otherwise, we can say, let's multiply both sides by C so that it clears the fraction. That means that we have C times the cosine of 62 degrees, and that's equivalent to 7.1. But if we want to solve for C, then we now need to divide. We need to divide both sides by the cosine of 62 degrees. So whatever we do to the left, we have to do to the right as well. So then if I want a calculation for C, I have to take 7.1 and divide it by the cosine of 62 degrees. So again, cross multiplication and division can help you do that more seamlessly, but this is a sort of fail-proof way of doing these calculations. So if we take 7.1 and we divide by the cosine of 62, what we get is 15.1 approximately. So I know my C value is approximately 15.1 units. Turns out that that side length is longer than the other two sides, and we would anticipate that because C is the largest angle. I also want to make mention that you could double check this now by using Pythagoras' theorem and seeing if a squared plus b squared was roughly the value we get for c squared. So there are always ways that you can double check some of the work you're doing when you're solving these types of triangles. Now that we have found all missing sides and all missing angles, we know that the triangle in this case has been solved. Before we move on to more problems, we're going to take a quick review of some terminology used in applications. So by applications, we mean word problems. We're going to be exploring some word problems that will require trigonometry for us to solve them. So the first two terms we would like to review here are the angle of elevation and the angle of depression. So when you have an angle of elevation, there are a couple of ways you might see this. An angle of elevation is always measured from a horizontal plane. So you see I'm sort of redrawing this horizontal line. Elevation means you're going to look upwards. So an angle of elevation is measured from the horizontal upwards. So we can see that one of two ways. We can see if you were looking at eye level and then your gaze went skyward, that would be an angle of elevation. Or we can think about being along the ground. If we have, again, a horizontal line, the angle of elevation along from the ground is going to be the angle required to see something above us. So those are the angles of elevation. Now, if you have an angle of depression, depression goes the opposite way. We still measure from the horizontal, but this time you are measuring downwards. So those angle measurements, again, are going to be based on the information we have from the application, but angle of depression is always measured from a horizontal line downwards. So if you could imagine starting your gaze or looking along that horizontal plane and then looking downwards to locate an object below you. So angle of elevation and angle of depression are two key elements that we'll be using as we work on some applications in the rest of this section. One thing that is worth mentioning is that if I sort of extend this picture that we have on the top side of your screen, if we have two lines that are parallel to one another, and we would assume if they're both horizontal that they are parallel. If we have something called a transversal running through it, so if we have another line running through that set of parallel lines, what we would note is that the angle of elevation in this picture and the angle of depression are actually the same. So if this angle measured, let's say 40 degrees, I would also know the angle of depression measured 40 degrees because we have two lines that are parallel and we have a transversal running through them. That might not be the case in the picture at the very bottom. It looks like those angles are the same, but we might have, let's say, 40 degrees on the top side as our angle of elevation, but maybe the bottom is only 38 degrees. Who knows? We can't assume that an angle of elevation and a depression are the same when they're coming from, let's say, a line of sight. But in the top side picture, because we have two or a set of lines that are parallel to one another, when you cross a parallel line with what we call a transversal, you create alternate interior angles. So 40-degree matches on both sides of that transversal. So we're going to use concepts like this when we, again, want to fill in information in order to solve applications. Aside from angles of elevation and depression, we have bearings and we have headings. So a bearing is measured very differently than a heading. So when you have a bearing, it measures the angle that the path of your object is going to make with what we call a north-south line. So there are different ways we're going to illustrate these kinds of measurements, and we want to start with some examples of bearings here. An example of some bearings would be things like north 20 degrees west, or we might give you another bearing as an example that measures south 30 degrees east. So in order to draw these properly, I highly recommend you start with your coordinate plane. So we know with a coordinate plane, you have north, you have south, you have west, and you have east. And when I draw these kinds of angles, or when I want to put them in their proper positions, where I actually place the angle measurement is critical. So if I want to go north 20 degrees west, in my mind, I sort of start at my point of origin and I travel north, which means I'm going to go upwards. And then we have to go 20 degrees to the west. So what I want to do is swing my pencil and drag it approximately 20 degrees towards the west. So when I drag my pencil, what it's going to show me is that's the angle that measures 20 degrees. So when I put my labels in place, it's going to be critical that my 20 degrees is hugging that space between my terminal side of that angle and the north-south line. So 20 degrees is sitting between where my direction of travel is and the north-south line. If I put that on the wrong spot, so if I put it underneath that line of travel, then I'm going to have an incorrect triangle with incorrect measurements. So what you see here in terms of labeling is north 20 degrees west. If we do the same thing and try and locate south 30 degrees east, or what direction of travel that would be, once again, you start with your north, south, west, east plane. And this time, instead of heading north, we are going to start from the origin and head south. So we're heading south or downwards. Then we want to swing to the east. So the east in this case means we're going to drag our pencil to the right. So if I drag my pencil to the right and sort of imagine I've created a 30-degree angle in that spot, we want to make sure that 30 degrees is marked between that north-south line and my new direction of travel. So this is how we would properly label and draw out specific bearings. Headings, on the other hand, are measured in a very different way. This is an angular direction, and it's basically another way we can illustrate which way a certain object is pointing or traveling. So this angle is actually measured clockwise from the north. What we mean by that is we might have some examples of headings here. I'll just give you two examples to work with. We might have an example of 120 degrees, or we might be given another heading measuring, let's say, 300 degrees. Recognizing that we don't have any north, south, west, or east directions, there's a norm for us when we draw out specific headings. When we talk about a heading of, let's say, 120 degrees, we have to start at the north line and rotate in a clockwise direction. So if I start along my north line and I rotate 120 degrees, I recognize that each quadrant is 90 degrees. So I'm going to travel 90 degrees to get through the first quadrant, and I need an additional 30 degrees before I reach my terminal side. So this would be an illustration of what we call 120 degrees. So we start from your north line and we need to rotate in a clockwise direction from the north. So the angle we've created there is 120 degrees. If we do the same thing for 300 degrees, again, we just need to have our north-south line essentially is the most critical line that we see here. But if we want to rotate 300 degrees, we know that every quadrant is 90. So start from your north line and make your rotation. So we've got 90 degrees, we've got 180 degrees, we've got 270 degrees, and we need to go another 30. So we've got a little bit further to go before we reach that terminal side. So this pink outside marking is showing us that that total distance is 300 degrees. What that does sometimes is it gives you the opportunity to fill in other missing angles. We know in a full rotation, our circle would make 360 degrees, so this wedge in between would of course measure 60 degrees. So sometimes we're not only given information, but we're able to use that given information to find other information. So once again, this is the difference between bearings and headings. Now to put all of this to practice, let's take a look at an application. It says in example number 3, a ship leaves port traveling south 65 degrees west. If it travels for 2 hours at a speed of 23 nautical miles per hour, how far south of port will it be? So what we need to do is come up with a picture that depicts the information accurately and start labeling the triangle that we'll create as much as possible. So if I know I'm going to leave port and I travel south 65 degrees west, in my mind I need to draw out one of our little coordinate planes here. So we've got north, of course, south, west, and east. Sometimes I'll do a really rough sketch and then I'll relabel a triangle so that it's more accurate and more clear. But in this case, if we need to go south 65 degrees west in order to see the line of travel, I'm going to start from my point of departure. That's my port. And I'm going to travel south, which is downwards, of course, and swing my pencil to the west, which means to the left. So if I drag my pencil roughly 65 degrees, this is my new direction of travel. Okay, so we know that the ship leaves port heading in this direction, south 65 degrees west. So I'd like to label that angle here as well before we lose track of it. So we know that this inside angle here is measuring 65 degrees. Now we know we travel for 2 hours at a speed of 23 miles per hour. So if I know that distance is always the rate multiplied by the time, 23 times 2 hours is going to give us a total distance of 46 nautical miles. So we can say that this is 46 nautical miles as a total distance. So I have one angle measurement and I have one distance so far. What they're asking is at the end of our 2-hour journey, how far south of port is this ship going to be? So if I draw a right triangle, and I can draw a right triangle here because I know that I want to know how far I am directly south of port. We've got a right angle measuring in this location. If we want to know how far south of port we are, we're looking for this side length here, and I'm just going to call that X for now. So we have technically the hypotenuse, and we're looking for a side now. Whether we call that adjacent or opposite depends on how we choose our reference angle. So again, it might be worthwhile for you to redraw the triangle that you're working with so that you can solve clearly and quickly. So I know we have 46 nautical miles as a side length. I know we have 65 degrees measured as an angle. And what I'm looking for here is an X value. I don't have to solve the whole triangle. That's not what they're asking for us to do. They're just wanting to know how far south of port we are. So what's that south or that north-south sort of side length measuring? So if we want to solve for just X and we want to label the sides appropriately, I know that 46 is the hypotenuse, and if we use 65 degrees as our point of reference or our reference angle, then we know X is going to be the adjacent side. So in order to solve for X, we can use a ratio that incorporates both adjacent and hypotenuse. So again, in the margin, you can see your SOHCAHTOA ratio tells us that cosine will give us the answer we need. So the cosine of some angle, and we can call that angle theta, is always the adjacent side divided by the hypotenuse. And in this case, we have the cosine of 65 degrees because that angle is known. That's going to give us the adjacent side of X divided by the hypotenuse, which we know to be 46. So from here to solve the problem, we can clear our fractions and multiply both sides of the equation by 46. So what we'll end up with now is an X value of 46 times the cosine of 65 degrees, and then that just becomes calculator work from here so that we can get our approximation. So if you type in 46 times the cosine of 65 degrees, what you should get as your final answer is approximately 19.4. And because this is an application, we want to put this together with a sentence. This 19.4 units is measured in nautical miles. So we can say the ship is approximately 19.4 nautical miles south of port after 2 hours. So once again, I'm not looking to solve the triangle. I only want one missing measurement in this particular case. Let's give our next application a little read here. It says, a plane flies at an average speed of 300 kilometers per hour on a heading of 170 degrees from an airport. How far east of the airport is it after 2.5 hours? So once again, I need to find a point of origin because we are traveling from an airport to another location. This time, instead of being given bearings, we're given a heading, and this heading is 170 degrees. So remember, when you measure headings, you have to measure from a north-south line in a clockwise direction. So we know that we've got 90 degrees in every quadrant, so 170 degrees is just going to be shy of that north-south line. So this is our direction of travel from the airport. From here, we know the plane is going to travel at 300 kilometers per hour and be traveling for 2.5 hours. So if you take that 300 kilometers per hour and you multiply by 2.5 hours, you get a total of 750 kilometers. So that's the distance for the leg of the journey. What we're asking for is how far east of the airport is this plane after that 2.5 hour mark. So once again, we can extend our triangle leg from the point of origin or from the airport until we get aligned with sort of the end of our leg of the journey for the plane. So I know our plane is still traveling in this direction, but if we want to know how far east the plane is from the airport, or due east it is, what we're looking for now is this x value. Now, I haven't put any angle measurements inside our triangle, but we actually know one of these measurements. If we know the outside heading was 170 degrees, and we know we're touching that line that makes 180 degrees total, then that little missing segment inside our triangle is only 10 degrees. Again, if that's hard for us to see, we can redraw the triangle. And we can relabel everything so that it's clear. We have 10 degrees in the top corner, we have 90 degrees in the bottom, and we have 750 kilometers as your hypotenuse. So if we're looking for how far east we are, once again, that's the base of the triangle that we're looking for in this case. So 10 degrees can act as my reference. I have an opposite side in x, so there's my opposite, and we know that 750 represents the hypotenuse. So if we look at our SOHCAHTOA ratio, using opposite and hypotenuse would require a sine ratio. So we can say the sine of our reference, which we know is 10 degrees, is going to be equivalent to the opposite side x divided by 750 kilometers as your hypotenuse. So once again, in order to solve this problem, we need to multiply both sides of the equation by 750 to clear the fraction. And when we do that, we get an x value of 750 times the sine of 10 degrees. So again, we just type that into your calculator, 750 times the sine of 10. That gives us 130.2 as your x value. And what we're talking about, once again, are kilometers. So we would say the plane is approximately 130.2 kilometers east of the airport after 2.5 hours. So once again, we weren't looking for all side lengths, just one side length in order to correctly answer the question at hand here. Our next application might be a little more involved, so take your time when you draw out these kinds of pictures. So in example 5, it says a surveyor is standing on a hill. So in my mind, I'm going to draw the little hill with a person at the very top of that hill. Aside from that, we're saying that surveyor notices that there's an angle of elevation to the top of a tower. So if they're looking up to see the top of the tower, then the tower must be taller than where they're standing. So I'm going to draw the tower, again as an approximation. So they're looking to the top of the tower and they have an angle of elevation. So if you can imagine that we have measuring from the horizontal, remember elevation is always measured from the horizontal upwards. So if you can imagine that this angle of elevation is where we're getting that 38.5 degrees, they also say that there is an angle of depression to the bottom of that same tower measuring 6.5 degrees. So it's okay that this is not to scale. We're just trying to sketch the information that we're given. So 38.5 degrees is sitting above that eye line or above the horizontal. 6.5 degrees is the angle measurement that is now sitting, oops, that looks like 65. Let's fix that here. 6.5 degrees is sitting as our angle of depression. So once again, that's measured from the horizontal downwards. So it's just that wedge of the triangle here. We also know that the surveyor is a horizontal distance of 32.6 meters from the tower itself. So this side length that is shared between these two triangles, if I can darken it here, that side length that's shared is measuring 32.6 meters. Now, I know that if I have a horizontal line and I'm meeting the side of a building, I would hope that that's square. So these would be 90-degree angles here. If I want to determine the whole height of the tower, I have two right triangles that we're going to have to utilize in order to do that. You're not quite ready yet to use other formulas to solve non-right triangles, so we have to use the two right triangles and combine our information. If we can find out sort of the top segment of this building, so we can call that X, and if we can figure out what the lower segment is or how long that segment is, we can call that Y, then we can combine X and Y to get the total height of that tower. So let's focus on X for a moment. If we want to focus on X and we use 38.5 degrees as your reference, X is going to be the opposite side, and 32.6 meters is going to be the adjacent side. So opposite and adjacent can be used with our tangent ratio. So the tan of, in this case, 38.5 degrees is going to give us the opposite side of X divided by the adjacent side of 32.6 meters. And again, we can cross multiply or multiply by 32.6 in order to clear this fraction. So multiply both sides by 32.6. We can see that that cancels. So X is exactly 32.6 times the tangent of 38.5 degrees. So when we type that into your calculator, 32.6, and you might want to double check these calculations or take your time when you're doing them, multiplied by the tangent of 38.5 degrees gives us roughly 25.9. So X is approximately 25.9 meters in terms of height. We now need to find Y. And if we find Y, again, reset your triangle. 65 degrees is now your reference angle. y is the opposite side, but the shared side of 32.6 is still the adjacent side. So we can use the tan ratio once again. So we can say the tangent of 6.5 degrees this time as your reference is the opposite side, or y, divided by the adjacent side of 32.6. So again, clear your fractions, multiply both sides by 32.6. So we get a y value this time of 32.6 multiplied by the tangent of 6.5 degrees. So we can get an approximation for y here as well. So 32.6 times the tangent of 6.5, be careful with your decimal, is going to be roughly 3.7. So again, it makes our picture look really funny, but we didn't know how big or how small those angles really were. I could have taken a little bit more time and drawn a more accurate sketch, but that's not the important part here. What we want to do now is combine that measurement with our previous measurement of 25.9. So when you add those together, because we want a total height, we know that the total height of the building is going to be 3.7 meters plus 25.9 meters. Or we can say that's a total of 29.6 meters. And of course, because this is an application, you'll want to tie that all together in a nice sentence. So we could say the tower measures, or the building measures, approximately 29.6 meters. Our last example says a plane is flying 2,500 meters above the ground. So if we have our lovely ground level, here's our plane. Our plane is way in the sky, and it's 2,500 meters above the ground. We can assume that, of course, we're measuring a perpendicular height to the ground. What we also note is that the plane is noticing that there's a building off in the distance. I don't know how tall the building is. It doesn't really matter how tall the building is, because what we're going to be doing is trying to figure out sort of a distance here. It says the angle of depression from the plane to the base of a building is 13.8 degrees. So remember, angle of elevation and depression are always measured from the horizontal upwards or from the horizontal downwards. So if this is an angle of depression, we need to measure from the horizontal downwards, because we're looking from the plane to the bottom of the building. That angle of depression needs to sit right here, and we know that angle is exactly 13.8 degrees. So there's your angle of depression. It's not giving us an angle inside the triangle, but we have different means in order to do that. So the only other piece of information we want to be mindful of is what the question is actually asking of us. It says, what horizontal distance must be covered, or must the plane cover, in order to be directly above the building? So if you want to imagine this triangle sort of extends, we're trying to find this distance x. You could also use the bottom part and say the distance along the ground would be the same horizontal distance. So it really doesn't matter which method you choose. I kind of like to use the one along the ground because I already have 2,500 meters as the height that plane is flying. So we do have some measurements that are missing but are easily found. If we take 13.8 degrees and we add a missing wedge, we know the total should be 90 degrees. So we have 76.2 degrees sitting inside that triangle. So again, that could be 90 degrees, which we know is the right angle that is met between your height and eye level. So if we take 90 degrees and we subtract 13.8, we've got 76.2 degrees missing on the inside of that triangle. We also know about alternate interior angles. Remember, if you have two lines that are parallel to one another, so I'm talking about the line along the top and the ground level here, so we're talking about the flight of the plane and the ground level. When you have a set of parallel lines that are intersected by a transversal, you have alternate interior angles that are equal. So if 13.8 degrees is sitting here, on the upper side of that transversal, then 13.8 degrees is also sitting inside here. So there are different ways we can come up with these angle measurements using properties of angle measurements in geometry. So we have more than enough information, pardon me, we have more than enough information at this point to solve the problem. If I want to solve for x, we can use 76.2 degrees as your reference, or we could use 13.8 degrees as your reference. If I use 76.2 degrees as my reference, let's say, x is going to be the opposite side, and 2,500 meters is going to be our adjacent side. So opposite and adjacent is a tangent ratio. So we would say the tan of 76.2 degrees is the opposite side of x divided by the adjacent side of 2,500 meters. So once again, this is just a quick little cross multiply or clearing of our fractions to solve. So to get an exact value for x, take 2,500 and multiply that by the tangent of 76.2 degrees. And again, just take your time doing the calculation. So 2,500 times the tangent of 76.2 is going to give you roughly 10,178.1. So x is, in this case, approximately 10,178.1, or actually 0.2, I guess, if we round properly to the nearest tenth, and that'll be meters. So our final statement would be something like the plane must cover a horizontal distance of 10,178.2 meters before it starts flying above the building in question. So in these kinds of problems, again, we're not looking for you to solve the whole triangle. We might be asking you to find only one or two elements within that triangle. Use your properties of geometry and use a really good sketch in order to help you choose not only the appropriate formula, but make sure your diagram represents the scenario clearly. So have a look at some of the practice questions here. This should say 10.2 exercises. So 10.2 exercises are going to include numbers 1 through 4, 8, and 9. So as always, if you have any trouble with these homework questions, please make sure you reach out and let us know. Always happy to help.